Hello, this is Dr. Kay Sweetser, and I would like to give you a little study guide for an SPSS output exam that you might be getting ready for. Before we get started, I want to remind you that there are two types of statistics that we're dealing with. We're dealing with descriptive statistics and inferential statistics. So descriptive statistics merely describe the data. Those are going to be things like your frequency, your mean, your standard deviation. Descriptive statistics do not have a p-value or any significance whatsoever. Now, inferential statistics are when you're taking those two or more variables against each other and you are getting a p-value. You are getting significance. You're looking at the relationship between those two variables. It might be the relationship in conjunction with one another, like a correlation where one goes up, one goes down. It might be some kind of a cause and effect type of relationship, like a regression might show. It might be breaking things up into groups and comparing means based on those groups, like a t-test or an ANOVA, but somehow you're going to get a p-value or probability associated with that statistic, and that is inferential statistics. Also want to remind you the difference between unidimensional and multidimensional constructs. So with unidimensional, it is only one big honkin' score. I cannot further define the concept into smaller pieces and parts. And then multidimensional, of course, I can get factors. So with unidimensional, I tend to have an index score, which is something like cred 1 plus cred 2 plus cred 3 plus cred 4, and then all of that equals credibility. However, with multidimensional, I would do a factor analysis and get several factors out of that. So now that we've kind of recapped the basics, let's go in and actually start to do some things that you might see on the exam. So you would not be asked to do anything like how do you get to this in SPSS? You would just be given some output, and from there you would have to say, whatever the prompt was. So for example, on this frequency that I just did on gender, I might say, what is the number of people who said that they were female? And so I would see 687 was the number of people who said that they were female. I might also say, of the people who answered the gender question, which percentage said that they were male. Now, when I start with of the people who answered the question, the key then is to come into valid percent, because you see, valid percent doesn't take into account all of these people who didn't answer the question at all, who skipped it. So when I say of the people who answered the question, I focus on the valid percent. And so if there was of the people who answered the question about gender, which percentage said that they were male, that would be 33%. If I just said what percentage of the respondents were female, then I'm looking at everybody. So I saw, okay, there's my male, my female is 58.8%. I also had a number of people who didn't answer the question, and those were included because I'm just looking for what percentage said that they were female in there. So be able to identify on a frequency the different numbers and know the difference between how they are set up and possibly be able to write a sentence about that. Now, the next thing I want to show you is going to be a mean. So we'll go ahead and do age, because age is a really good mean here. With a mean, remember, you're always going to have means and standard deviations together. So with means and standard deviation together, I don't care that there were 24 people who were 31 years old. What I care about is right here in this statistics box. So I see that the mean is 40.41 years old, and the standard deviation was 15.33 years. So that's how big my groups are apart from one another, my standard deviations. So just be able to look at a statistics box and know how to locate the mean and the standard deviation. And then if I were to write this in a sentence, I would say the average age of the respondent was 40.41 years old, and then in parentheses I would put my SD equals 15.33 in there. So that's mean and standard deviation. Again, these were descriptive statistics. So let's go ahead and move to our inferential statistics. So one of the first inferential statistics that we deal with would be an independent samples t-test. Know when you do an independent samples t-test, and know why you do an independent samples t-test. So with the when, it would be when you're looking for I guess the when and the why are the same there. When you're looking for a difference between two different means. And so if I want to know based on gender, which might be my grouping variable, I'm going to have a nominal level variable in there. My gender is set up as 1s and 2s. And then I take some kind of an ordered variable, be it ordinal, interval, or ratio, some kind of a higher level variable, and I put it in my test variable. And so this will tell me if men in this response set seem to be more, have more age or less age than women. Okay, so in here, in my t-test, the first thing that I want to look for is my p-value. You have a lot of different p-values here in the independent samples t-test. So I have a sig right here and I have a sig right here. What I'm looking for is the sig two-tailed, and if you can kind of see this line coming up right here, this is one type of test, and then all of this is for the other type. And so I care about this one, the equality of means. And so I go into sig two-tailed, and I'm assuming equal variance is assumed, and this is my sig right here, which is comes up as perfect. Of course, we never report that as perfect. We report it as 0.001 anytime you have a p-value of 0.000. And I'm going to go ahead then and say that this significance meets the threshold. Recall that our threshold is 0.05, so it has to be less than 0.05. So I know that whatever differences I see here in this independent samples t-test is going to be legit. These differences are real. And so I was doing a test to see whether who was older and who was younger in this group, looking at the average age of women and the average age of men. So then I come up, now that I know that the difference is statistically significant here, I come up and I look at my scores here, and I see that the average age of men in this group were 47.89, and the average age of women were 36.38. And so with this, I would be able to say that the women in this group were significantly younger. And notice I mean significantly in the way of statistical significance, not that it was important that they were younger. So be very careful with your language there. So this is a t-test, and with the t-test you have a nominal variable and then you have a higher level variable like ordinal, interval, or ratio. And you're looking at the difference between two means. Now another type of means test, of course, is an ANOVA. And with an ANOVA, you're looking at the difference between 3 or more means. I'll try that one. Oops. So with this one, I do have to set up a post hoc test. A post hoc test accompanies every ANOVA because a post hoc test is going to tell you where the difference lies between the two, or I'm sorry, where the difference lies between the group comparisons. The post hoc tests that I like to use are either Bonferroni or Tukey, and you won't be needing to set this up, so all you have to do is learn how to read this. So the first thing that we do with an ANOVA is we look at the overall ANOVA box. This is a survey asking people in public relations about their jobs, and so I have my higher level variable. My ratio level variable in this case was how long have you been in your current industry. And then my nominal variable, the categories were what type of employer do you work for, a sole practitioner, an agency, nonprofit, corporate, government, etc. So in here, I first look at my statistical significance in the ANOVA box, and I see that it's 0.000. I'm going to report that as 0.001. And this is good significance. So this means that whatever I find within my ANOVA is going to be a marked difference, a significant, or it's going to be real. So I'm allowed to go on. So as I go down into my post hoc test, this is going to tell me the difference between the two groups. And the post hoc test is going to literally compare one cell to another, one cell to another, one cell to another, and so on and so forth. And then it's going to go through and it's going to do the next one where you will see repeats. You notice that this number is the same as this number because we're comparing sole practitioner versus agency. And then in the next big section, it's agency versus sole practitioner. So you will have repeated numbers in here. So what I'm going to do is I'm going to look through this SIG column right here, and I'm going to try to find any statistically significant differences. And I see I got a bunch of them right up here at the very first sections. Sole practitioner versus agency is significant. Sole practitioner versus advertising agency. Sole practitioner versus nonprofit / association. And sole practitioner versus corporate. So these are all statistically significant. I have column I here, column J, and then the mean difference I minus J. So if this number in here is a positive number in this column, then that means that the sole practitioner, the one over in column I, is actually the higher number. If this number in this column is a negative, it means that the item in column J is the higher number. So I see sole practitioner minus agency has a mean difference of 10.74 years in the industry. So to me that says the sole practitioner has been in his work industry for 10.74 more years than the person who just worked in the agency. If I do sole practitioner minus corporate worker, I see that the sole practitioner has been in his industry 7.06 years more than the person in corporate. This kind of makes sense because if you're going to go out on your own, you've probably done work for other people in other organizations first before you strike out on your own to become a sole practitioner. So these results make sense as well. So the things that I want you to be able to know with ANOVA is I want you to be able to tell me if the overall ANOVA is significant, and I see my significance right there. I want you to be able to tell me which of the cells are statistically significantly different from one another, and I find that by looking at the SIG over here. I want you to be able to tell me what the SIG is for that pairing, and then I want you to be able to tell me what the mean difference is, and then which one is higher. Recall also that this is an inferential test, and that every time you do an ANOVA, you have to do a post hoc test. The post hoc test is going to be the thing that tells the difference between the actual cells. So you must be able to do that. We'll go ahead and now do a correlation. Correlation refers, of course, just to the relationship that the two variables have with one another. Correlation does not equal causation. So as I look at my correlation table here, the first thing I look at is significance. And I see that my significance is 0.000. I'm going to report that as 0.001. And I see that my correlation value, which ranges from a -1 to a +1, is 0.18. So this is a very, very weak correlation. I tend to not report correlations unless they are at the 0.3 or above level. The higher or closer this number is to a 1, be it a -1 or a +1, the stronger the correlation. So if this were like a 0.8, this would be a really strong correlation. However, it's a 0.18. Super, super weak. So be aware of that. So those are the things that I'd want you to know. I'd want you to know the R value and be able to find it on your correlation table. This R value is 0.18. I'd want you to know whether this was good or bad as an R value. You would tell me it's bad, it's weak, it's below 0.3. I want you to be able to tell me what the significance is. It's 0.001. And I'd want you to tell me whether that significance is good. And you'll say the significance is good because the p is less than or equal to 0.05. So this is a good one. Getting a little bit more complicated, the next thing I'm going to show you is not a test, but it is the data preparation, which is a factor analysis. We use factor analysis when we are doing multi-dimensional data, and this will tell me what constructs exist with the things that I'm looking at here. So you would not have to know all of the different boxes to click in here, and of course the way that I know which boxes I'm clicking comes through me actually looking at how this thing has been done in the past. So with factor analysis, I would not show you any of the boxes that don't matter. I would only show you the boxes that do matter. And the first box that I would look at would be my total variance explained box. A couple of things for us to know here that I would ask you. I would ask how many factors are there? And you're going to see it goes all the way out for factor 1, all the way out for factor 2, and then it stops. All of this white space means it stopped working, it stopped creating factors. So this would tell me that this is a 2-factor solution. The next thing I would do is I would ask how much cumulative variance or how much variance is explained by this 2-factor solution. And you would go into the cumulative column and you would say, okay, at the end of factor 2, we see that we have 61.81 cumulative variance explained. And so that's my answer, 61.81% percent of the variance is explained. Then I would ask you if this is enough. Yes or no? And the percentage of cumulative variance that has to be explained in order for this to be multidimensional is 60%, 60. So this is meeting the threshold. So this 2-factor solution is good. This 2-factor solution works. So then the next thing that I would ask you to do is to go down into the actual factoring model, and for you to be able to look at these factor loading scores and tell me which factor a particular variable is in. So I might say rel 23, which is right here, which factor is rel 23 in? And so you would go over here and you would look for which of these factor loading scores are higher, and I see it's higher and it is above 0.3 in factor 2, so I would say rel 23 belongs to factor 2. I might ask you, what is the factor loading score of rel 25? So I'd have to go in here and I'd look for rel 25, it's right up here. Rel 25, I'd look again, which number is higher? I see the first, it's highest in factor 1, so I would say the factor loading score is 0.75. I might say how many variables are in factor 1. So I would say this is a factor 1, so 1, 2, 3, 4, 5, and then I get here and all of a sudden I'm switching over to factor 2, so I would say there are 5 variables in factor 1. And that is just about all of the things that I would ask you here. I might ask you to look at an alpha score. Remember, your alpha has to be above 0.7 for it to be good, and then you can always improve an alpha by deleting specific items, but I tend to not want to delete items unless my alpha comes out beneath the threshold. So for the exam, know the threshold, know some basic definitions, know when I'm setting up a test, what types of variables do I use. So for example, when I'm doing a correlation, they both need to be those higher level variables like interval, ordinal, or ratio. Know that when I'm doing a t-test or I'm doing an ANOVA, it needs to be a higher level variable, and then I need to have a nominal level variable in there because that's the way that I'm cutting the data, male versus female, or type of organization that I work for, government, corporate, etc. That would be a nominal. And then know the thresholds. So my thresholds for significance, 0.05. My threshold for reporting a correlation, I want it to be 0.3 or higher. My threshold for factor analysis, I need to explain at least 60% of the variance. And my threshold for my factor loadings, which should be higher than 0.3. So this is how you totally win at your awesome SPSS output. Make sure you look in your course pack as a study guide and watch this video as often as you need. It's not going to be hard. It's going to be very easy, and you'll be able to totally ace this bad boy.